Quantum heat engines are advanced devices that utilize the principles of quantum mechanics to convert heat into work, much like classical heat engines, but with significant differences due to the unique properties of quantum systems. At the heart of a quantum heat engine are quantum particles such as atoms, molecules, or qubits, which can exist in multiple states simultaneously, superposition, and can be interconnected in ways classical particles cannot, entanglement. To understand how a quantum heat engine works, consider a classical steam engine. It absorbs heat from a hot reservoir, converts part of this heat into work, like moving a piston, and releases the remaining heat to a cold reservoir. A quantum heat engine operates on a similar principle but uses quantum states instead of steam and pistons. For instance, a quantum heat engine might consist of a single ion trapped and manipulated by lasers. The ion can absorb heat, undergo quantum state changes, and do work on its environment by shifting its energy levels. An analogy to grasp this concept is to imagine a playground swing. In a classical engine, the swing moves back and forth in a predictable manner, converting the push, heat into motion, work. In a quantum engine, the swing can exist in multiple positions at once, superposition, and pairs of swings can be perfectly synchronized, entanglement, allowing for more complex and potentially more efficient conversion of heat into work. Examples of quantum heat engines include setups where quantum dots, tiny semiconductor particles, interact with thermal reservoirs to produce electrical work, or systems where trapped ions are used to demonstrate fundamental thermodynamic cycles like the Carnot cycle in a quantum regime. These engines not only push the boundaries of efficiency, but also provide insights into the fundamental nature of energy and work in the quantum world. The story of quantum heat engines is intricately woven into the larger tapestry of quantum mechanics, a field that has revolutionized our understanding of the universe. It all began in the early 20th century, a time of great scientific discovery and innovation. Physicists, grappling with the behavior of light and matter at the atomic level, were on the brink of uncovering new realms of knowledge. They stumbled upon a reality far stranger than they could have imagined. Pioneers like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg shattered the foundations of classical physics, challenging long-held beliefs and opening new avenues of thought. They revealed a universe where energy came in discrete packets called quanta, fundamentally altering our perception of reality. These groundbreaking discoveries laid the groundwork for quantum thermodynamics, a field that explores the interplay between quantum mechanics and thermodynamic principles. In 1959, Scoville and Schultz-Du Bois proposed the first theoretical model of a three-level maser as a quantum heat engine, a concept that would pave the way for future innovations. This marked the birth of quantum heat engines as a distinct field of study, setting the stage for decades of research and technological advancements. Why are scientists so excited about these tiny engines? What makes them so special and groundbreaking? The answer lies in their potential to revolutionize various fields, from energy to computing and beyond. Quantum heat engines hold the key to unlocking unprecedented efficiency in energy conversion, making processes more sustainable and cost-effective. Imagine capturing waste heat from industrial processes and transforming it into usable energy, reducing waste and improving efficiency. Their potential applications extend far beyond energy harvesting, impacting numerous sectors and industries. In computing, quantum heat engines could lead to quantum computers that are exponentially faster and more powerful, capable of solving complex problems in seconds. These quantum computers could revolutionize fields like medicine, material science, and artificial intelligence, leading to breakthroughs we can only imagine today. At the nanoscale, quantum heat engines could power tiny sensors and actuators, ushering in a new era of nanotechnology with applications in healthcare, manufacturing, and more. The development of quantum heat engines is still in its early stages, but the potential rewards are enormous, promising to transform our technological landscape. As we continue to unravel the mysteries of the quantum world, the future of quantum heat engines is brimming with possibilities, offering a glimpse into a more advanced and efficient future. To grasp the significance of quantum heat engines, we must venture into the realm of quantum thermodynamics. This field explores how thermodynamics principles play out in the microscopic realm of atoms and photons. Classical thermodynamics deals with systems in thermal equilibrium, where temperature is well defined, but in the quantum world, things get much weirder. Quantum systems are inherently probabilistic, with quantized energy levels. Concepts like temperature become fuzzy at the quantum level. Quantum thermodynamics seeks to describe the flow of energy and the performance of work in the quantum regime. It's a field pushing the boundaries of our understanding of both thermodynamics and quantum mechanics. Section 5. Quantum engines, Otto, Carnot, and more. The quantum realm offers an array of quantum heat engine designs, drawing inspiration from classical counterparts. One example is the quantum Otto cycle, a quantum analog of the four-stroke engine. This engine undergoes quantum adiabatic processes, interspersed with sudden changes for energy extraction. Another key player is the quantum Carnot engine, setting the ultimate efficiency limit for any heat engine. Beyond these, researchers are exploring quantum Stirling engines, quantum Brownian motors, and more. Each design offers a unique approach to harnessing quantum effects for energy conversion. Section 6. How quantum engines work, from theory to reality. The inner workings of quantum heat engines might seem like science fiction, but they rely on fundamental principles. The key difference lies in the quantum realm. Imagine a quantum system, perhaps a single atom or photons confined within a cavity. This system possesses discrete energy levels, like rungs on a ladder. By manipulating the system's interaction with its surroundings, we can induce it to climb or descend these energy levels. Heat can be supplied to the system, causing it to absorb energy and climb to higher levels. Work can be extracted by allowing the system to release energy and descend to lower levels. Section 7. Quantum engines in the lab, challenges and triumphs. Translating theoretical concepts into real-world devices is a formidable challenge. Building and controlling systems at the atomic level requires extraordinary precision. Experimentalists have made remarkable strides, demonstrating rudimentary quantum heat engines in labs. These experiments provide tangible evidence that harnessing quantum phenomena for energy conversion is possible. However, maintaining the delicate quantum coherence necessary for operation is a persistent challenge. Quantum systems are susceptible to noise and decoherence, which can degrade performance. Despite these challenges, the field of experimental quantum heat engine research is brimming with excitement. Section 8. Powering the future applications of quantum heat engines. The potential applications of quantum heat engines extend far beyond fundamental physics. QHEs could enable us to tap into vast reserves of waste heat and convert it into usable energy. Imagine capturing the heat generated by electronic devices, industrial processes, or even the human body. In computing, QHEs could pave the way for quantum computers that are exponentially faster and more powerful. These quantum computers could revolutionize fields like medicine, materials science, and artificial intelligence. At the nanoscale, QHEs could power tiny sensors and actuators, ushering in a new era of nanotechnology. The possibilities are limited only by our imagination. Section 9. The road ahead, future directions, and innovations. The field of quantum heat engines is still in its infancy, but the road ahead is paved with exciting possibilities. Researchers are exploring more robust and scalable QHE designs. Future QHEs will need to be more practical and efficient for real-world applications. Novel quantum materials and systems could enhance QHE performance. The theoretical understanding of quantum thermodynamics is constantly evolving. Researchers are developing new frameworks to better describe and predict QHE behavior. Section 10. Quantum leaps and breakthroughs, case studies in QHE research. The field of quantum heat engines is brimming with exciting research and groundbreaking discoveries. In 2016, researchers at the University of Oxford demonstrated a miniature heat engine powered by a single calcium ion. This tiny engine showcased the potential of harnessing quantum phenomena for energy conversion. In 2018, researchers at the University of Waterloo developed a theoretical framework for a quantum heat engine that could achieve Carnot efficiency. Their work demonstrated how engineered quantum systems could surpass classical efficiency. These case studies highlight the remarkable progress being made in QHE research. Section 11. Exploring the quantum world. Resources and inspiration. The world of quantum heat engines is accessible to anyone curious about quantum mechanics and thermodynamics. Numerous resources are available for those eager to delve deeper into this fascinating field. Academic journals like Physical Review Letters and Nature Physics regularly publish cutting-edge research on QHEs. Online repositories like ArXiv provide access to preprints of scientific articles. Books like Quantum Mechanics, The Theoretical Minimum by Leonard Susskind and Art Friedman are great starting points. Online platforms like Coursera and edX offer courses on quantum mechanics and thermodynamics. Documentaries and videos on quantum mechanics provide accessible and entertaining introductions to the quantum world.